Alright, let's look at some examples of some discrete time systems. This is from section 3.4 of your text. We'll look at just some classic examples. First we'll look at a model for computing the amount of money you might have in your savings account. Some definitions here. X of n is our input function. So these are deposits that we would make at instant n. And then y of n is our output. It's the account balance, so the amount of money we have in our account. And then finally, R is the interest rate. So this is the interest per dollar per interval. So this might be, on a yearly basis, in which case, n equals 0 would be our starting year, and then when n is equal to 1, it's a year later. Or we could do it on a daily basis or a monthly basis, depending on how we defined our interest rate. So y of n, our current account balance, is equal to the amount we had the previous year plus the interest rate times the amount we had the previous year plus any new deposits that are made this year. So we can rewrite this as 1 plus r times y of n minus 1 plus x of n. And then just to simplify the notation a little bit, I'll define 1 plus r as being equal to a. So I can rewrite this as y of n minus a y of n minus 1 is equal to x of n. Again, where a is equal to 1 plus r. Okay. And there's some similarity between this equation and equations we looked at in the continuous time chapter, similarities to differential equations. This is what's known as a difference equation. So we will be looking at, in this chapter, some solution methods for difference equations. With these discrete time systems, the system can be implemented either in hardware or software. What's interesting is that we can always solve these difference equations exactly using recursion or iteration. So as an example, let's let r equal 0.05, it's 5% interest, and I'll model our deposits as we start with an initial deposit of $100, and then I'll add an additional $100 2 years later, and I want to calculate how my account grows. Again, a is 1 plus r, or 1.05, and then from my difference equation, I have y of n is equal to a times y of n minus 1 plus x of n. Okay. And then, so I can just use this equation to start counting, to start calculating my account balance. At y of 0, it's going to be a times y of minus 1. So this would be an initial condition. I'm assuming that my account starts with 0 balance, and then plus x of n, which x of n at n equal to 0 is equal to 100, so y of 0 is 100, and that's my starting balance. Okay. Y of 1 is a times y of 0, so that's 1.05 times 100 plus x of 1. X of 1 is 0. It only has non-zero values at n equal to 0 and n equal to 2. So in the second year, my account balance would be 105. Y of 2 is a times y of 1 plus x of 2. So x of 2 is 100, and then so I'll have here 1.05, which is a, times y of 1, which is 105, then plus the additional deposit of $100. So this turns out to be 210.25. And then similarly, I can calculate y of 3 using y of 2 and y of 4 and so on and so forth. Okay, so I can always use this iterative method to calculate the output of a discrete time system, but we're often interested in finding a closed form solution, a formula for y of n in terms of n. So we'll look at some solution methods for doing that. I'll also mention that we can model our system using a block diagram, just as we can do for continuous time systems. Our system equation here is x of n plus a y of n minus 1. So block diagram look like this. And we have our x of n sequence as input. We're adding to that a delayed version of y of n. Okay, so here's my output y of n, and I'll represent a delay here with just a D operator. So this takes as input y of n and produces as output y of n minus 1. I also have to multiply that by a. I'll just show that next to a little arrowhead here, and then these two are summed together. So we can see that this block diagram is a representation of this particular equation. Let's take a look at another example system, a digital difference machine or digital differentiation. And in this case, the output is, we'll define it to be 1 over some constant t, where t is the time interval between our samples, and then a difference between two adjacent samples, our current sample and the previous one. So this would be a discrete time approximation to the differentiation of x of t. And then similarly, we can have a digital integrator. Approximation in this case just becomes, the integration becomes a sum. We multiply the sum by our time interval, summing from k equal minus infinity to n of x of n this would be, I guess, equivalent to, rectangular numerical integration, where we assume x of n stays constant between sample intervals. I can actually write this in a slightly different form. Y of n minus 1 would be equal to, I'm just going to sub n minus 1 for n, t sum from k equal minus infinity to n minus 1 of x of n. So I can write y of n, which is a sum from k equal minus infinity to n. I can treat that as a sum from k equal minus infinity to n minus 1, which is y of n minus 1. And then just plus my current sample, x of t times x of n. So I can write this in the form now of, this would be my recurrence relationship. If I take the y of n minus 1 term to the other side, I get my, it's not a differential equation, but it's a difference equation. And here it is in recursion form. So the recursion form would allow me to compute successive values of y of n. And let me conclude this lecture without going into any detail because of similarity with previously covered material, but we will be looking at working through several homework problems in the lecture period. Classification of discrete time systems. So a lot of the same classifications that we talked about with continuous time systems. We can have linear and nonlinear discrete time systems. We can have time invariant, non-time invariant systems. We can have causal and non-causal systems, invertible and non-invertible, stable and unstable, and then finally memoryless and then systems with memory. And we'll look at solution techniques in subsequent lectures. The methods we'll concentrate are applicable to time invariant linear systems or linear time invariant systems, often abbreviated LTI. These other characterizations will apply, and we'll be able to we'll want to be able to determine if a discrete time system is causal or non-causal or stable, unstable, etc. But the solution techniques we'll look at will work for any of these characterizations, but the systems have to be both linear and time invariant, at least to be able to calculate the output using convolution.